by having this example that says that we have in the center a sphere that has a charge negative Q. That sphere is non-conducting. It's an insulator, and it's surrounded by a conducting shell, metallic shell. And this is case 1. In case 2, we just removed that conducting shell. We removed it. So you have only the sphere. Then the first question here was, we need to compare the electric field before and after we remove the shell. So what to do? So again, I'll say it one more time, guys. Pay attention to what I say. We have in the center, we have a sphere that's non-conducting sphere that has a charge negative Q, and it's surrounded by a spherical shell. That's a metallic spherical shell that has a charge that's uncharged. Does not have any charge. It has 0 charge on it. And then we remove that conducting shell and we leave the sphere by itself, and we need to compare the electric field at that point before and after we remove that conducting shell. So what to do? So what to do? So we'll study each case by itself. We'll draw Gauss's sphere or Gauss's surface around at Gauss's surface in such a way that the point that we need to find the electric field at is located on the surface. Then apply Gauss's law. And when we go and apply Gauss's law in the first case, this is the sphere that has a negative charge Q, and it's surrounded by a spherical shell. And we need to find the electric field at that point. So we draw Gauss's surface, then go and apply Gauss's law that states that the integration over a closed surface for E dot dA will equal to the charge inside Gauss's surface divided by epsilon 0. Okay? One good thing about Gauss's surface is that the electric field all over Gauss's surface is constant. It does not change. So if the electric field is constant, it goes out of the integration. The area of Gauss's surface, that's 4 pi r squared. That's r. Equals to the charge inside Gauss's surface. What is the charge inside Gauss's surface? Negative Q over epsilon 0. And from that, the electric field will equal to minus 1 over 4 pi epsilon 0 Q over r squared.
So 1 over 4 pi epsilon 0 over K?
Yes. So that's the electric field in case 1. Now, remove that shell. To do the same thing again, we draw Gauss's surface in such a way that the point that we're trying to find the electric field at is located on Gauss's surface. Then write Gauss's law and try to apply it. Now, the electric field on Gauss's surface is constant, so the electric field goes out of the integration. The integration over dA, that's 4 pi r squared. Now look at Gauss's surface. Even if the shell is not there, what is the charge inside Gauss's surface? It's the same charge, negative Q. So you get the same electric field. So the answer for part A is B. The two electric fields are equal. Okay? Now, let's look at B. What is the surface charge density sigma 1? This is very important. This is a nice one. So I'm going to erase that, and let's concentrate only on the assembly that we have. We have a charge Q in the center, and if you have a charge negative Q and you bring any material closer to it, what happens to that material? It gets polarized. It gets polarized. And I mean by it gets polarized that if this is a positive charge on that surface, you get a negative charge equal to that amount of the charge. So if you have a Q in here, you get on that surface Omar negative Q, and on the other surface you get positive Q. So if we apply that in here, this shell, it's going to get polarized. So you'll get here positive Q and you get here negative Q. And then the positive Q is going to be distributed on the inner surface, and that negative Q is going to be distributed on the outer surface. Now, what is the sigma? Sigma is the surface charge density. Surface charge density, which is Q over the area. Sigma N, sigma on the inner surface, is the charge on the inner surface divided by the area. So that's sigma N. Look at it. Is it positive or is it negative? So which one is the answer? C. How about the outer surface? It's going to be negative Q divided by 4 pi R2 square. That's R2. Which one is higher? Sigma N or sigma out?
Sigma. They're both the same, but they're not the same.
Which one is higher?
The sigma.
Well, I get two answers. They are both the same, but negative. Which one has higher surface charge density? Which surface has higher surface charge density? What do you mean by the first one? The inner one. The inner one. And simply because they have, both of them have the same amount of charges, but here the radius is much smaller than the radius, so sigma N is more than sigma L. Magnitude, regardless of the charge. So good. We solved that in class. If you have infinite wire that's very long, and again, guys, infinite, that's something relative. So if you have a wire that's 1 meter long and you're trying to find the electric field 1 millimeter away from it, then the wire will look as if it's infinite wire. So if we have a very long wire, that's the wire in the middle, and we need to find the electric field at a distance R from the wire. What to do? I'm going to follow the same method that we have applied on the sphere. That's the wire. We did that before. When we start talking about Gauss's law, we did that problem. So I'll do it again, very fast. Then, this wire has a charge Q. What to do? Draw Gauss's surface, and obviously we have, what kind of symmetry do we have in here? Cylindrical symmetry. So I'm going to draw a Gauss's surface, or Gauss's surface to be a cylinder. That's Gauss's surface. It has a radius R. That's where we need to find the electric field at. We said that we have to choose the Gauss's surface in such a way that the point that we need to find the electric field at is located on the surface. And it has a length of h, for example. This is the length of Gauss's cylinder. Now, apply Gauss's law, the integration of E dot dA will equal to the charge inside Gauss's surface divided by epsilon 0. Right? Good. The electric field is constant. Am I right? Yes, this is one good thing about Gauss's surface. The electric field all over Gauss's surface is constant. So it goes out of the integration. What is the integration over that surface? Oh, before I go into that part, doing the integration, I need to know which surface actually I'm interested in. The round shape, that surface or that surface? And the round shape, the reason for that is the electric field from that wire. The electric field from that wire is always in that, if this is positive charge, it's always in that direction or that direction. This is the direction of the electric field. And the reason for that, if you take any two segments in here, that's the symmetry. And you find the electric field at that point, for example, the X components will cancel out and only the Y component will survive. So we know that if you have an infinite wire, the electric field from that wire is going to be perpendicular to the wire. That direction. But there will be no electric field along that direction. Okay, guys? So so the E dot dA for that surface is 0, and E dot dA for that surface is also 0. We're only interested in the round shape. So the area of the round shape is times 2 by RH will equal to the charge inside Gauss's surface. What is the charge inside Gauss's surface? No. Q is the charge on the whole wire. It's the charge per unit length times the length of Gauss's surface. So it's lambda H divided by epsilon 0. H will cancel out. And you can calculate E. You can find E. That's easy. Now, guys, I'll go back to this wire again. Now we have an infinite wire. What is the direction of the electric field from that wire? It has a charge Q. It has a charge Q. What is the direction of the electric field from that wire? It's radially out of the wire. So this is the direction of the electric field at that point. And at that point, this is the direction of the electric field. At that point, this is the direction of the electric field. At that point, what is the electric field? 0. Good, thank you. Yes, there is no electric field along that wire. This is if the wire is infinite. But if it's a short wire, it will have some field on the two ends. And we'll get to that later. Okay, guys. Sorry, I don't have so many wires we need, so I will assume that those are wires. I'm going to assume that all of those are wires. This is the first wire, second wire, third wire, fifth, and so on. So I'm going to continue doing this till I fill the whole table by wires. Now, what do we have?
A plane.
A plane. Thank you. A plane. So if you get wires and you stack them closer to each other, all of them, you get a plane. What is the direction of the electric field from that plane? Up. Or down? Yeah, it has to be perpendicular. So again, proving that the electric field from the wire is always perpendicular to the wire. If we stack so many wires, very thin wires, you will form a plane. The electric field from that plane is going to be either in that direction, up, that plane, the table, or down. So it's going to be perpendicular to the plane, yes.
How thin should the wires?
Assuming that you have infinite plane. So the plane, the x and the y dimension of the plane is much, much longer than the distance that you're trying to find the electric field at. So but if I'm trying to find the electric field at that point from that table, no, this is not going to be an infinite plane. But if you're trying to find the electric field at that point from that table, this is an infinite plane. Okay, Abdullah.
How thin should the wires be to consider it adding them up a plane? Like how thin should it be?
0, almost 0. The radius of that wire. It has to be very, very thin.
We're assuming that the wire has no thickness?
No, it has a guys, it's just I'm trying to actually to tell you, to simplify to you what is a plane. It's just many lines. A plane is just many lines. In that case,
It's a very thin line?
yes, it's a very thin wire. But even if it's a thick wire, we'll study a thick wire in a minute. Okay, so now we know that the electric field from a plane is going to be outside of the plane if it has a positive charge, and if it's a negative charge, it's going to be into the plane, like what we did for a positive and negative charge, point charge.
Not to the plane and that thickness or not?
Yes.
مش هو اللي هيبقى تحت هيكمل فوق.
What?
يعني for example if you have هيبقى فيه هنا واحد صغير كده واحد هنا they will cancel each other يبقى فيه
We'll see. We'll go to the plane. But before I actually, I just wanted to, since we're talking about a wire, a line, an infinite line of charges, I said that's a good idea to introduce the plane. Then now we're going to do it. We'll take more examples on infinite wires or cylinders that carry the charge. Cylinder has a thickness. Then we'll go into details to the plane. Okay. Okay, a good way actually to test if we get the knowledge or not is just to give a quick quiz. This is not a quiz, but we'll solve it together. Guys, we have a line charge, that's the closed line in the middle, that has a charge per unit length equal to lambda. And how did I know that this is the charge per unit length? It's the units, thank you. Is placed along the axis of uncharged conducting cylinder. So there is around it there is there is uncharged metallic or conducting cylinder. It has a radius, inner radius A, and it has an outer radius B. What is the value of the charge density sigma 0 or sigma O, which is the charge density on the outer surface?
So that's basically a shell.
Yes, yes, cylindrical shell. We need to find the charge density on the outer shell, on the outer surface. We need to find the charge density on the outer surface. Yes, yes, you have a wire that has a charge per unit length equal to lambda. Then you have around it a cylinder. A cylinder around. And we need to find what is the charge density on the outer surface of that cylinder. Outer surface. Excuse me? The outer surface. And you can see that we have 3 answers. So let's vote on them. ممدوح. So what do you think?
But the line has the positive charge or negative?
It has a, since I did not mention that it is negative, you can see that it has to be positive. Omar, right? So what? What do you think? Either A or B. Okay, so it's not 0. You're saying that it's not 0. It's not going to be 0. Yeah, Omar is saying it's not going to be 0. The answer is either A or C. Attabi is saying it's C. Marina? How about you just guide me through it? What to do? And it's okay, we all make mistakes. I make mistakes most of the time, not only you. So tell me. Just guide me. What I'm supposed to do? I need to solve that problem. I have three solutions and I cannot cheat from my neighbor, so I have actually to solve it myself. So tell me what to do.
Well, we have to find the
what's going to happen if you have a charge? If you have a charge Q, then you bring another material close to it. What are you going to do for that material? There is a phenomenon that's going to happen in here, and we call it polarization. And we mean by polarization that charge, if it's positive charge, it's going to attract the negative charge on the inner surface, and it's going to attract and it's going to repel the positive charge on the outer surface. So this is positive. Okay, that's positive charge, so it's going to attract the negative charge on the inner surface, and it's going to repel the same amount of charges to the outer surface. Now, if this has a charge Q, how much charge will be on the inner surface? Minus Q. And how much charge are we going to have on the outer surface? Positive Q. That's easy. Wait. Okay? Do we all agree on that? Good. So I know that Q M equal to the charge on Q on the wire. I know that the charge on the inner surface equal to negative of that Q on the wire. Negative of it. And the Q on the outer surface will equal to the charge on the wire. And since we are interested in the outer surface, so I'm going to concentrate only on that Q. How much charge do we have on the wire? It's lambda times L, whatever the length of that wire. So we know that the charge on the outer surface is lambda L. Now, sigma, which is equal to Q out, sigma out, Marina? Sigma out, that's the charge per unit surface, which is equal to the charge on the outer surface divided by the area of the outer surface. What is the area of the outer surface? 2 by B, 2 by B, L. So, which one is the right answer? C. Okay, guys? Good. Plane. Sharif, I'm going to start by having only a very thin infinite plane. Very thin infinite plane that does not have a thickness. And Sharif, if we have an infinite plane that has a thickness, then this is not an infinite. Infinite means that the dimension in x and y is much more than its dimension in z. So we almost ignore the dimension in z. So if we are talking about infinite plane, so it's by default it's very thin. Okay. Now we need to find the electric field from that plane. This is going to be a surprise for you guys. What to do? Again, we have to choose Gauss's surface carefully, apply Gauss's law, and that's it. So what kind of Gauss's surface should we have? What kind of Gauss's surface? Actually, if this is the plane, I can choose a cube to be my Gauss's surface. So if I choose cube to be a Gauss's surface, part of it inside out in that side, and the part of it in the other side, since it's a very thin plane. So I'm going to choose a cube. Half of the cube is out in here, and the other half is in here. Or I can choose a cylinder, anything that has planar symmetry. And here we have a planar symmetry. And the two ends of the cylinder, we have a planar symmetry. So either you choose a cylinder or a cube. I'm going to start solving the cylinder because it's on the presentation. Then we'll solve it by having a cube to be our Gauss's surface. Okay, guys? Okay? Can we choose a sphere? No. Sphere does not have a planar symmetry. You have to have the same symmetry of the surface. But cylinder, those two bars are planes. You have the same kind of symmetry that the surface has. Okay, so now I have chosen my Gauss's surface to be a cylinder. Let's find the electric field. Let's apply Gauss's law on that. Yes. Yes, I need to find the electric field at that point. That point. At a distance x. At a distance x from the plane. Here. This is the plane. This is the plane. I need to find the electric field at that point. So I choose my Gauss's surface to be this. Cylinder, this. And the other part of the cylinder is on the other side. On the surface. It has to be on the surface. Yes. On Gauss's surface. Okay? Okay? So if this is the plane, then this is going to be our Gauss's surface. We need to find the electric field at that point, Sharif, at that point, which is on that plane, on that surface of the cylinder. What is the direction of the electric field? It's going to be into that direction or that direction. This is the direction of the electric field, and we agreed on that.
And you have this on the diagram?
Excuse me? Yes. And I got that by assuming that the surface is just composed of so many wires, and with knowing the direction of the electric field from one wire, I can extrapolate that to the direction of the electric field from infinite plane. Okay. Now, let's apply Gauss's law. E is constant on Gauss's surface times the area. Which area are we talking about? The two caps. Not the round shape. Because the area of the round shape is perpendicular. Yes. is parallel, the direction of the area of the round shape is parallel to the electric field. So you get 0. No, I'm sorry, perpendicular. Perpendicular. The area here is that. This is the direction of the area, perpendicular to the area. And so it's perpendicular to the electric field, so the dot product for that round shape will give you 0. So the area is going to be pi r squared. This is r times 2 equal to Q enclosed divided by epsilon 0. What is the charge inside Gauss's surface? No, it's not a length. It's not a length. It's not a wire. Again, remember. So this is the plane, guys. This is the plane. Look at it. Do you see the area of the plane, Omar? Do you see the area of the plane that has charges? That pinkish area? Do you see it all? This is only the area that's inside Gauss surface. No. What kind of shape do you have in that pinkish shape? It's what? It's surface. It's pi r squared. Only pi r squared. So Q inside is going to be sigma times pi r squared. What's sigma? Who said that? We asked about sigma. Sigma, that's a constant. We should know it actually when we try to solve problems in using Gauss's law. We should know either lambda, which is the charge per unit length, sigma, which is the charge per unit area, or rho, the charge per unit volume. Those are the 3 charge densities that we talked about. Okay, now look at this. E times 2 pi r square equal to sigma by r square divided by epsilon 0. Pi r square will cancel out. E will equal to sigma over sigma over 2 epsilon 0. This is the electric field from infinite plane. Okay, this is the electric field from infinite plane. Look at it. Does it depend on the distance from the plane? No. Yes? Who said yes? Who said yes? No, it does not depend on the distance from the plane. So this is a finite plane. That wall is an infinite plane, and we're trying to find the electric field at that point. It's going to be sigma over 2 epsilon 0. At that point, it's going to be sigma over 2 epsilon 0, and so on. As long as this is infinite plane. So it does not depend on the distance. Omar?
How come it doesn't get weak in the electric field?
Because that's infinite plane. It goes from negative infinity to positive infinity along the x.
This direction.
Yeah.
And if you go there times 2 kilometers,
Yeah, and 2 kilometers compared to 2 billion kilometers. What does that mean? If you go 2 kilometers, then this is not infinite plane anymore. Then it gets weaker.
depending on this.
Yeah, well, my assumption that this is infinite plane, and my assumption means that the dimension of that any dimension of that plane is much smaller than the point that you're trying to find the electric field at.
Any dimension is much bigger than this.
Yes, that's by definition what we mean by infinite plane.
Why
Okay.
isn't it infinite plane if we go 2 kilometers this way?
Because that's if this is infinite plane, then this is that dimension is 2 times 10 to the power 300 kilometers, and you're going only 2 kilometers. This is infinite compared to that. Okay, this is too long compared to that 2 kilometers that you're talking about. Got it? Okay. Now going back to Heba's question, where did the tooth come from? sigma over 2 epsilon 0. Where did the 2 come from? Yeah, because we have two areas. We said that this integration will equal to E times pi r squared plus 0 plus E times pi r squared. Guys, can you explain that? Can you explain that? What did I do?
Yeah, the 0 is actually the round part.
Yes. It's the electric field, that integration, which is the flux, by the way. Let me use that terminology again. This is the flux. This is the flux, by the way. Guys. So the flux over that surface, it's E times the area. That surface, that dark one. The flux over the round shape equals to 0. That's the 0. I divided that into 3 areas to simplify for you to know where did the 2 come from. Then plus the other side, it has an area of pi r squared, so the flux is going to be E times pi r squared, which is equal to the charge inside Gauss' surface, sigma times pi r squared, divided by epsilon 0. So this is going to be E times 2 pi r squared equal to sigma times pi r squared over epsilon 0. You get E times equals to sigma over 2 epsilon 0. Why 2? It's a very thin plate. Almost has 0 thickness. And so it's a very thin sheet, and we need to find the electric field on that sheet. It's a sheet, it does not have a volume. It's a sheet. And the charge on it is going to be the area, the charge on that inside Gauss' surface. This is more important. This is the important thing. You're trying to find the charge inside Gauss' surface. It's that circle that you see inside. What is the area of that circle? It's the area times the sigma. That's why it's sigma times the area. Okay? Okay. This is good. This is most of the confusion comes from that point.
Doctor, can we find this charge infinite plane in reality, or it's just imaginary thing?
Dina? Say that,
Can
Kareem.
we find this charge infinite plane in reality, or it's just imaginary thing?
This is the reality. If you have a do you know what is a capacitor, guys? We're going to study that. We're going to study it. So a capacitor is just a plate that has a positive charge and another plate that has a negative charge, and the distance between them is very, very small distance, and the plate is the dimension of the plate is much smaller than the distance between the two plates. So the area between the two plates, the electric field in it is constant, and we consider that plate in that case as an infinite plate. So this is a real application for what we have studied now, a capacitor. Okay? Okay, good. So what we did on the board is we have proven that E equal to sigma over 2 epsilon 0. And that means that the electric field from infinite plane is independent of the distance. It does not depend on the distance. This is a constant electric field. Do you remember, guys, someone was asking me about, do we have a constant electric field? Yes, this is a constant electric field. So if we want to draw this electric field, if I want to draw this electric field, yes. Thank you. So if this is the plane, this is going to be the electric field. Equidistant lines, so something like this. That's an electric field from that plate. If it's a positive charge, if this carries a positive charge, and if it carries a negative charge, negative charge, then the electric field is going to be into the plate. Capacitor. Two infinite sheets. Now I will have two infinite sheets. Sheet number 1, sheet number 2. One has a charge positive Q, shady. One has a charge negative Q. And we need to find the electric field between those two plates and outside of them. Electric field. Oh, I'll do it, don't worry. And if I don't do it, you'll find it in the homework. So do not worry. Okay, we'll do that. Then we'll do the cube. We'll find the electric field if we choose Gauss surface to be a cube instead of a cylinder, and I think we'll end the day. We'll end it for today. Okay. So, any ideas? Any ideas what to do? Positive Q. Can I do that? And we need to find the electric field at point 1, point 1, point 2, and point 3. Can I do this? Can I do it with two different colors? This is the negative one. I'm going to do it blue. I don't have blue with me. Okay, green. And the positive one, I will do it with red. Any ideas? Yes, yes.
Two Gauss cylinders.
Okay. Okay. And thank you. This is what exactly I'm going to do. Omar said, well, find the electric field at any point of interest from the first plate and the second plate as vectors, then add them. Okay? Omar, from the first plate, what is the direction of the electric field at that point? Sorry, at that point. Direction.
Going up.
Okay? What is the magnitude of that electric field? Sigma over 2 epsilon 0. We just did it. Okay? From the second plate, Omar, what is the direction of the electric field?
The other way.
What is the magnitude of the electric field? No, you take, oh sorry. The magnitude, because I put the direction already. The negative will dictate the direction. So if we put a direction by an arrow, you should take the absolute value for the surface charge density. That's a good thing. What will cancel out? Oh, yes, that's a totally different story. Yes, yes.
Are they going to cancel out?
Yes.
Are the radius different?
Wait. Okay, are you follow? Okay, now what is the total electric field? E total, according to Omar, he said that it's E1 vector plus E2 vector. This is going to give us 0. Because the electric field number 1 is along that direction, and it's a sigma over 2 epsilon 0, and electric field number 2 is along that direction, and it's also sigma over 2 epsilon 0, so they cancel out. So the electric field at that region, at any point in that region, is equal to 0. Same thing in here. How about in the middle? What is the direction of the electric field from the plate, from the positive plate? That's E1, and it's sigma over 2 epsilon 0. What is the direction of the electric field from Actually, from the negative plate, it's into the plate, and E2 is equal to sigma over 2 epsilon 0. Excuse me? Okay. Heaven. From the first one, it's because this is positive, it's out of the charge. From the second one, because it's negative, it's going to be into the charge. This is the direction of the electric field. That's why the. Excuse me?
You concentrated on the green one for now.
No, I'm trying to find the electric field from the two plates. The red one, which is the positive plate, infinite plate, it will create a electric field out of the plate. So the electric field from that plate, it's going to be this direction and that direction. The electric field from the negative plate is going to be along that direction. Sorry. It's into the plate. This direction and that direction. The electric field is into the negative charge and it's out of the positive charge. So now add the two electric fields, E total. What's E total? 2 sigma over 2 epsilon 0, which is sigma over epsilon 0.
So Doctor, 2 epsilon E,
Guys, Shadi?
Q over
Omar?
sigma equal Q.
Oh! When I say Shadi, Omar, I don't have to call everyone by his name. And if he asks something and you ask it again, okay guys, I'm going to follow that policy. If you talk and someone asks something and you ask it again, I'm not going to answer it. Okay. 2 epsilon 0. Okay, that was the first thing, that when we had only one plate and we drew Gauss's surface and we applied Gauss's law and said that that plate has a surface charge density of sigma, then the integration of E dot dA equal to Q enclosed divided by epsilon 0. This integration is actually E times pi r squared, that area, plus 0, which is E dot the area of the round shape, plus E times r by r squared, which is that area, equals to Q enclosed. What is the charge inside Gauss surface? This charge, it's sigma over sigma times pi r squared, sigma times the area over epsilon 0. You get here 2 E pi r squared equal to sigma by r squared divided by epsilon 0. This is the electric field from one only infinite plane. But if you have a couple of them, one of them carries a charge, positive charge, and the other one carries a negative charge, then the electric field between them is going to be sigma over epsilon 0. And the direction of that electric field is going to be from the positive charge to the negative charge. It makes sense. That's what we have studied before. Abdullah?
Mathematically, okay, it makes sense that the R cancel each other out, so we don't take it into consideration when we're calculating the electric field on the side. Okay, it makes sense, but without calculation, how is it possible? Or would it thought directly that here is something that, you get what I mean?
You mean outside of the two plates? It makes sense. Remember that we're still talking about infinite plates, that they carry the same amount of charges. So one of them is going to create an electric field in that direction, and the other one is going to produce an electric field equal in magnitude and then the opposite direction, because they carry different type of charges.
plate and the distance between them is very
Yes,
small.
and still you're trying to find the electric field outside them. At a small distance outside them.
And small distance between them too. So it's
Yes,
actually
yes,
the same
yes,
thing.
yes, 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 yes. And this is what we mean by infinite. When we say infinite, then any other dimension is much smaller than the dimension of the plate. Okay? And actually, in reality, when you try to measure the electric field outside, you find some electric field outside because no matter what, if you go a little bit far away from the plate, you will find some electric field. It's not going to be zero. That's in reality. There is another way actually to solve this. Remember, when we from one plate, if you take Gauss' surface, guys, if you take Gauss' surface to have the two plates, and if you try to find the electric field here and here, here and here, what is the total charge inside Gauss' surface? This is, forget that cylinder. For that cylinder, what is the total charge inside Gauss' surface? What is the total charge inside Gauss' surface?
That's what that.
Zero. Yes. How do you know that it's zero? How did you know that? Opposite signs. Maureen, right? Maureen is saying, well, it's zero, and she's surprised that you cannot get the answer. So she said that plate will have a positive charge, sorry, negative charge, and that plate will have a positive charge, but since they have the same areas, they will carry the same amount of charges, then they will the total charge inside Gauss' surface is zero, and if the total charge inside Gauss' surface, then the electric field on Gauss' surface is going to be zero. So the electric field here is going to be zero, here is going to be zero. This is another way to prove it, other than what I put in the whiteboard. So now I believe that you can solve number 4, number 5, and 6 in the assignment number 2, and those should be due on Thursday.
Number 4 and
5 and 6 only. 5 and 6 only. Yeah. 5 and 6 only. 4 is what? 4 years should have been submitted today. So guys, this is just a revision for what we have done so far. Guys? Yes. Thursday. When is the exam again? We moved it to Tuesday, right? So let's have the Tuesday. I can postpone that assignment number 3 to Saturday. We have a class. Saturday. We have to. No, why? It's going to be before the exam and we'll have some revision. Why not? Actually, and I can spend some more time with you. Come late and plan to spend some more time with me if you have someone to pick you up. Or we can start earlier. We can start at 2 if you want to. So we can do some revision before the... Maureen, I can start on that Saturday. I can start a little bit earlier. I will come solve problems. And whoever wants to come, they can come. But at 3, we'll start our regular class. Okay, guys. Now, do you have anything regarding this? No. I'm gonna review what we have studied so far. We have 3 kinds in Gauss. When we go and apply Gauss's law, Dina, when we go and apply Gauss's law, are you done? Should I start? if we go and apply Gauss's law, then we have three kinds of symmetries. Spherical symmetry, and we choose our Gauss surface in that case to be a sphere. Cylindrical symmetry, and we choose our Gauss surface in that case to be a cylinder. And planar symmetry, and we also choose our Gauss surface in that case to be a cylinder. We can choose a cube and I will do it. This is a very nice problem in here. Do you have the solution, guys? The solution is going to be on the presentation. Read it, and try to explain it to me. I will pick someone from you guys. Maybe I will start with Amir Hosni. Next time, then Lena, and what's your name? And Mufaddal. Lena. So Amir, then Lena, then Mufaddal. Then guys, at least you should meet the three of you and talk about that problem, because I'm gonna ask you about it next time. And that does not mean that there will be, I will ask only Amir, Lena, and Mufaddal. I might ask anyone else. Okay? Now, cube. The cube. I'm going to prove that the same problem again using a cube. Plane, infinite plane that has a charge, surface charge density sigma, and we need to find the electric field everywhere. ممدوح؟ This is my Gauss surface, a cube, which I don't really prefer, but we'll do it. Because some of you might think that this is much easier than a cylinder, which is not actually, but let's do it. Yeah.
Why don't you prefer it?
Because it does not really have the symmetry that it's more clear with the cylinder. I will show it to you in a minute. Now, let's apply, this is Gauss's surface. Let's apply Gauss's law. This is Gauss's law. Now, which side has a flux? Four sides? Are you sure? No. Hey, relax guys, relax. Just relax. Does anyone have a book? Physics, chemistry, those heavy books? Anything? No, that's enough. Good enough. Okay. Assume that this is the cube. I have it. Thank you. Assume that this is the cube. This is the plane. This is the cube. Part of it is out, and part of it is in here. Okay? Side 1, 2, 3, 4, 5, and 6. Which one has a flux? Which side has a flux? That one, the top, and the bottom. So this is the plane, this side, and that side. The other, they will have, the electric field is actually perpendicular to the direction of the area. Perpendicular to the direction of the area, and we have agreed, since few of you guys send me definition of area, that and they all agreed that area can be a scalar and it can be a vector. So those two sides only have flux. So this is the flux, which is going to be E times the area, whatever the area is, I don't care, equal to, what is the charge? Actually two areas. That one and that one. No, this is the plate. This has zero flux. This has zero flux. This has zero flux. This has zero flux. Because the electric field is in that direction. And the direction of the area in here is that. And the direction of the area is here is that, so they also perpendicular. The direction of the area in here is this, so still have perpendicular, same thing. But in here the area is in that direction and the electric field is in that direction. Okay, parallel. Top and bottom in here, right? Left and right in there on the board. Because this is the plate. This is the plate. This is the plate. So E times 2A. Okay, Abdullah. E times 2A equal to Q enclosed. What is the charge inside Gauss' surface? What is the charge inside the surface? It's sigma times that area.
Which area?
That area. Which is the area of a face of the square, any side of the square. That's what? No, that's not a line. No, it's not a wire. It's a plane. It's a plane. Same thing that we did in here. We have been talking about a plane for the last 45 minutes. Over epsilon 0. Do we get the same answer? Yes, sigma E equals sigma over 2 epsilon 0. Why don't I like this? Because sometimes you get confused, you get more sides. You get confused about which side gets zero flux. Cylinder is much easier. Though at the first time it looks like it's not easier, but actually it's much easier. Actually, at least to imagine it. Okay guys, okay, thank you so much for coming. I'll see you, pick up your